Hello students, in last lecture we have seen the excess carrier generation and recombination. So in this lecture we will see the excess carrier lifetime. In semiconductor, the electrons in conduction band of the material may make transition from conduction band to valence band. That is, the electrons recombine with the holes in the valence band. This recombination may be either direct or indirect. So in direct recombination, the excess population of electrons and holes decay by electron falling from conduction band to valence band. So the electron, let's say this is the conduction band edge denoted by EC, and this is the valence band edge denoted by EV. So when electron in conduction band may make transition and recombine with the hole, then this process is spontaneous process. That is, no any external force or no any external agency is required for this recombination process. When the electron from conduction band falls to the valence band and recombine with the hole. So the energy lost during this recombination process, that is, when the electron from conduction band falls to valence band and recombine with the hole, the energy is lost and it is given out in the form of photon of energy h nu. That is, this probability that an electron and hole will recombine, it will be constant in time because this process is spontaneous. As in this case, the carrier scattering with the constant probability, which leads to an exponential solution for the decay of excess carriers. So in this case, the rate of decay of electrons at any time t is proportional to number of electrons remaining at time t and the number of holes with the proportionality constant alpha r, which is the proportionality constant of recombination. So the net rate of change in the conduction band electron concentration is the thermal generation rate, that is alpha r Ni square minus recombination rate. So the net rate of change in conduction band electron is given by dNt by dt, which is equal to thermally generation rate, that is alpha r into Ni square minus the recombination rate, that is alpha r into Nt into Pt. So this is equation number 1, where this alpha r into Ni square is the generation rate. This is the generation rate, and this alpha r into Nt into Pt, this is the recombination rate. recombination rate, and this alpha RNA square is thermal generation rate. So in this way, the net rate of change in conduction band electron concentration is this difference between thermal generation rate and recombination rate. So let's assume the excess electron hole population is created at time t is equal to 0. So at time t is equal to 0, the initial excess electron and excess hole concentration are equal. That is, excess electron concentration which is given by delta n, and excess hole concentration at time t is equal to 0 is given by delta P. So let's consider this excess electron concentration and excess hole concentration are equal at time t. So we may write delta n is equal to delta P. Okay. So as this excess electron concentration and excess hole concentration initially are constant, then as electron and hole recombine in pair, the instantaneous concentrations of excess electrons and excess holes are also constant. So instantaneous concentration of electron is given by delta nt and instantaneous hole concentration is given by delta pt. So the instantaneous electron concentration and instantaneous hole concentration will be equal if the excess electron and excess hole concentration are equal. So thus we can write the total concentration of this equation number 1 in terms of equilibrium concentration. That is, equilibrium concentration is given by P0 and N0, and the excess carrier concentration, these instantaneous excess carrier concentrations when this delta nt is equal to delta pt, and in terms of this excess carrier concentration, one may write this equation number 1 as d by dt of delta nt which is equal to alpha r ni square minus alpha r into bracket n0 plus delta nt into P0 plus delta Pt. So again we may write this as it is equal to minus alpha r into n0 plus P0 into delta nt plus delta nt square. So this is equation number 2. This is d of delta nt by dt. So This non-linear equation can be simplified for the case of low level injection. If the excess carrier concentration are small, we can neglect the term delta NT square. Delta NT square can be neglected if excess carrier concentration are small. If the material is extrinsic, we can usually neglect the term representing equilibrium minority carriers. For example, if material is p-type, that is, if material is p-type, one may write P naught is greater than N naught. So, if the material is p-type, this equation number 2 becomes, this is the equation number 2, and it becomes d by dt of delta NT which is equal to minus alpha r into P naught into delta NT. So this is the equation which represents the excess carrier concentration for p-type material, and the solution of this equation is an exponential decay from the original excess carriers delta n. So the solution of this equation is given by delta NT which is equal to delta n into e raised to minus of alpha r into P naught into T, alpha r into P naught into T. So which is equal to delta n into e raised to minus T upon tau n. So this is equation number 4, where this tau n is the carrier, excess carrier lifetime of electrons in p-type material, and which is given by alpha r P naught inverse. So this tau n is also called as recombination lifetime, recombination lifetime, or it is the excess carrier excess electron lifetime in p-type material, and this tau n is given as, it is equal to alpha r into P naught raised to minus 1, or it is inverse, that is tau n is equal to alpha r P naught inverse. Also one may write the excess whole lifetime tau p which is equal to alpha r into N naught inverse. So this is the whole that is excess whole lifetime in n-type material. So it is also called as minority carrier lifetime, and the decay of excess holes in n-type is given by tau p is equal to alpha r into N naught inverse. So in this case of the direct recombination, the excess majority carriers decay at exactly the same rate that of the minority carriers. So the approximation of extrinsic material and low level injection allows us to represent Nt in equation number 1 by the excess carrier concentration delta Nt. This excess carrier concentration is delta Nt. So one may write in general the carrier the lifetime, that is excess carrier lifetime, which is given by tau n, which is equal to 1 upon alpha r into n naught plus p naught. So this is the excess carrier lifetime, which is given by tau n is equal to 1 upon alpha r into n naught plus p naught, and this expression is valid for the n type as well as p type material if injection level is low. So this gives the excess carrier lifetime for the extrinsic material. So with this I will stop here. Thank you.